Dr. Seager, can you please tell us what got you interested into astronomy in general, and more specifically, looking for planets orbiting other stars in the sun and eventually for life on those planets?
One of my first memories is of the moon. I was in the back seat of the car as my father was driving, and the moon wouldn't stop following me. It's always there. I just couldn't figure out what was going on. And when I asked my father, he didn't know. He didn't have an explanation. But in some ways that's a good thing because it keeps one thinking. Later on, I was about 10 years old, and I was on my first camping trip in Ontario. And I stepped outside the tent at night and looked up, and wow, there were so many stars I didn't even know that existed before. And ever since then, I just was enamored. I loved the sky, I loved astronomy. But when I went through the teenage years and such, I didn't really pay attention in school. I wasn't really that into science. But I think astronomy was always brewing in the back of my mind. And actually, I started to study when I was in high school and pay more attention, and I learned about chemistry and a bit of physics. And then I actually joined the Royal Astronomical Society of Canada in the Toronto Centre, and I started attending the meetings. I even got to take an astronomy class in the evenings, which was one of the highlights, literally, of my teenage years. So I think I always loved astronomy. Now, one day, I was 16 years old, and I went to the open house at the University of Toronto, right near where I lived, so I knew there was an open house. And I went in there, and it was one of the, I would say, top 5 days of my entire life, because I realized one could be an astronomer for a job. I had no idea that you could do this for a job, as a living, do research and do astronomy. So I was so excited. I rushed home and I told my father, and he was angry. He gave me a long lecture, and he would say things, he told me basically, Sarah, you can't rely on any man. You need a job where you can support yourself. And he was worried that in astronomy, it's a good worry, I think, that you might not have a job. There might not be a job in what you want. But the good news, what I learned was that undergraduate physics degree students are rarely unemployed. Usually they're fully employed. They might not be employed in physics or in a job that they had set out to do, but with that kind of quantitative background, and that's even more true at the PhD level, pretty much all of them are employed. So I knew that if I went down that path, I would get something. I don't know what would happen, but I could pursue astronomy. And at that point, I decided when I was accepted to the University of Toronto, and I went in there and I studied math and physics. Astronomy is more of an application, so it's good to study the fundamentals. And I got to have a summer job at the David Dunlop Observatory, where I studied variable stars, taking data with telescopes. We didn't have CCDs back then. It was just, well, now I'm going to age myself, but there weren't CCDs, but we still used 2 telescopes on the roof of the administration building. One was looking at the target star, and one was a comparison star. And I'd have to set one off and go set the other off, and in the meantime, find the stars in the little guide telescope, and then set it all off going and stuff. So I did that for a couple of summers. And then I was admitted to Harvard for graduate school. And I arrived at Harvard, I did a master's, the equivalent of a master's thesis, and I was looking around for a new topic for my PhD. And lo and behold, exoplanets around sun-like stars had just been discovered about a year earlier. And my PhD advisor said, Sarah, why don't you try this? It's interesting. He didn't have enough time to work on it himself, so he wanted to give it to me. Now, normally, one would never give a student such a risky project. At the time, there were about 4 or 5 exoplanets known, including 51 Peg. And these were hot Jupiters, planets the mass of Jupiter, orbiting very close to their star. They were orbiting 10 times closer to their star than Mercury is to our sun. And most astronomers, rightly so, because we're supposed to be skeptical. You know, if people come to you and announce some new phenomenon, you want to know what is going on here, what's really happening. And a lot of people didn't believe they were planets. They thought it was a new type of stellar pulsation, all sorts of explanations. And so I decided to work on it anyway, though, since I was a risk taker and I felt like I had nothing to lose. I may as well do something interesting. And as the years went by, the skepticism decreased. When the first transiting planet was discovered, there was no question that was a planet, because at the time the rate of velocity measurement said the planet would go in front of the star. It went in front of the star, as shown by photometry and the drop of brightness of the star. And so then many more planets were found, planets that were far enough from the star that they couldn't be explained away by a stellar pulsation. And the field of planets started to boom. And because I'd worked on it, kind of since day one, not since the early people who worked on developing the techniques to find planets, but since I'd worked in the field ever since it had first started, I was right on top of the game.
And now you're looking for life on those planets that we're starting to discover. What clues do we have, or might we have, of the presence of life on those planets? What betrays the presence, or what could betray the presence of life on those planets?
Well, to fast forward from finding the first planets to studying their atmospheres, we now have incredibly ambitious goals. And what we want to do is look at the atmospheres of small rocky planets and look for signs of life in the atmosphere by way of what we call biosignature gases. There's two answers as to what are we looking for. One is we can describe our terrestrial biosignature gases in great detail. And the second answer is we actually really don't know what we're looking for. But back to the first answer, we're looking for gases that don't belong. And on our planet, our best example is oxygen. Oxygen is produced by plants and photosynthetic bacteria. We have oxygen in our atmosphere to 20% of our atmosphere by volume. But without life, we would have almost no oxygen. Such tiny amounts that for the capabilities we have, we'd never be able to see a planet with no life. We would have such small amounts of oxygen that it basically would barely be detectable from afar. So actually, oxygen is an example of a gas that is produced like 10 orders of magnitude out of equilibrium, as in the case of no life. And so while there are some false positives, some ways to produce life, some ways to produce oxygen without life, we hope that we can sort through those if and when we find oxygen on another planet. But in general, we're following a decades-old concept of looking for gases that don't belong, that are produced in so much quantity that it's hard to figure out any other explanation than life itself.
Now, if and when we discover something that doesn't belong, what happens? What's next?
Well, it's going to be a lot of work actually, because hopefully it will be easy to find gases that don't belong. Hopefully we can build and launch sophisticated space telescopes and see gases in the atmosphere and robustly detect molecules and identify the molecules and the gases and the abundances. But we have many things to follow up on. Once we find a gas that doesn't belong, we'll have to look at the other gases present and try to understand what's going on in terms of all the gases and how out of equilibrium it actually is. And after that, you have to use your imagination of what we'll do next. We may want to consider studying that planet in a lot more detail, observing it for a few months, instead of just the day or the week that it might take to get a spectra, to watch it more carefully and see what else we can see on the planet. We may decide we have to launch an even bigger space telescope and maybe pass that on to the next generation to construct and launch a bigger telescope to not only see the biosignature gases in more detail, but to look for other gases, like we call them technosignatures, gases like chlorofluorocarbons that are certainly only produced by intelligent life. They're not naturally occurring. So we could have that option as well.
Do you have any kind of collaboration between your team and the teams that are looking, for example, for radio signals or laser signals coming from eventual other civilizations?
Right. So there's another whole group of people looking for signs of communication from intelligent life directly or indirectly. Right now, the extent of the collaboration is that people who are searching for radio signals that might be coming from another planet that might have intelligent life is that they're focusing on planets that we have discovered. So the Kepler Space Telescope found untold numbers of small planets, and they actually listen in on those stars right now. So that's the collaboration that we have with them.
And those planets and planet candidates that Kepler found, do you have any, without selling the punch of course, do you have any interesting prospects in there?
We take care to distinguish between candidates and confirmed planets, but we believe that for small planets, Kepler's false positive rate is quite low actually, so we're pretty confident that most of those Kepler planet candidates are actually planets. There's many interesting planets in the Kepler bunch. I think the most interested one for people at large is Kepler 186f, which is the first Earth-sized planet in the habitable zone of its star. The habitable zone is the so-called Goldilocks zone, where a planet heated from the outside is not too hot, not too cold, but just right for life. Kepler has a lot of other fascinating planetary systems, but that one is the one that they say is both Earth-size and in its star's habitable zone as we know it.
Do you have a spectrum of this planet?
That's a good question. Now, the Kepler small planets, they're actually too small and too far away for us to get a spectrum of. And in exoplanets, we often have to separate out discovery from characterization. So Kepler discovered a bunch of planets. Its goal was to count planets, how common are small planets. But the planets are unable to be followed up with spectra because they're too far away and too faint. So we don't have spectra of those. And in fact, if you want to know the truth, we don't have spectra of any planet that could remotely be considered habitable. We're just not there yet, technologically speaking.
Do we have any spectra, period?
Yes. So when you think of all the pieces of the puzzle, we have spectra, we have studied planet atmospheres, dozens of planet atmospheres. These are big hot planets, Neptune-sized or Jupiter-sized planets, typically very close to the star. We also have found many small planets that we believe are predominantly rocky, but those we can't get the atmospheres for. So in some ways we have every piece of the puzzle, but we're still reaching down to the smallest planets.
So we're still missing a few pieces of the puzzle.
We are. And what we're missing, we hope that we will recover part of the missing piece of the puzzle with the James Webb Space Telescope. It's going to launch in 2018. And now we've been studying atmospheres of giant planets. We believe the James Webb will have the capability to study the atmospheres of much smaller planets.
Now you said we don't have the technology yet. How long until we do?
Well, there are two answers to the question, how many years until we have the technology to find the Earth-like planet? There's two ways to do it. One is going to happen now. It's planned. It will happen. We're going to discover a pool of planets, transiting planets around small stars. And those planets, we can look at their atmospheres with, we will say, tried and true techniques with the James Webb Space Telescope. And it's MIT is leading a NASA mission called TESS, Transiting Extrasolar Planet Survey Satellite. That's kind of like a different form of the Kepler Space Telescope. It will do an all-sky survey looking for small planets transiting small stars. And from those planets, we'll find some ideal candidates that we will use the James Webb Space Telescope to look at their atmospheres. And transiting planets are very special because the planet goes in front of the star as seen from Earth, or as seen from the telescope, rather. And the starlight shines through the atmosphere in a way that we can pick up the planetary atmospheric species. And so that way we have that planned. We're all excited. We're all working hard on that problem. But transiting planets are rare. The planet has to be lined up just so, as seen from the telescope. And we may run out of ideal candidates. There may not be enough ideal candidates for us to really have a great, robust shot at finding signs of life. So the second approach is totally different. And that actually involves a technique we call direct imaging, which René Doyon here in Montreal is a pioneer in this field from the ground, but we'd like to go to space so we can reach down to Earth-like planets. Now, an Earth in reflected light is very faint compared to its star, 10 billion times fainter. So what we effectively need to do is block out the starlight so we can see the planet directly. This is a huge challenge. This is way harder than anything we've ever done in astronomy before. But astronomers around the world, and particularly in the United States, are working hard on this problem. And so that's our next step.
So 20 years, 25 years?
Well, I can give you a really specific answer to that. So with the James Webb Space Telescope, it will launch in 2018. And a few years after that, we should have been able to observe all the atmospheres of the ideal planet candidates. So what I'd like to say is that if planets with life are very common around small stars, very common, if the planets are very common in the habitable zones, which we believe they are, and if the planets all have life and most of that life generates a spectroscopic signature, we actually have the capability to find that. If it's true that life is ubiquitous in generating spectroscopic signatures we can detect, we'll find it.
Oh, so less than 10 years.
I'd say with the Earth twin and blocking out the sun-like starlight, that one, if we had enough money to do it, we know how to do it. And again, if Earths are common, we believe we have the capability to solve this problem if we had. And right now I'm chairing a NASA study. There's two studies ongoing called probe class studies, and we are asked what can we do for a certain amount of money in a certain time frame with regards to direct imaging with the small space telescope. And we're studying a telescope between 1 to 2 meters in diameter, quite small actually. And in our case, we would be using a star shade to go with the telescope. A star shade could be launched together or separately. It's a 30-meter in diameter, very specially shaped screen, and it would fly tens of thousands of kilometers away from the telescope to block out starlight so only the planet light enters the telescope. Now it's quite complicated. People have been working on this the concept arose in the 1960s, and in the last decade, technology in terms of the shape of the star shade, how it would stow, how it would deploy, formation flying, have all been worked out to great detail. And we know how to get from where we are today in technology development to be ready to build and launch. And we believe that we could do that by starting in 2017 and launching in 2023. That's what we were asked to study. We believe it's doable if we get funding to do it. And then give us another 5 years after that. So certainly with the Earth twin technique, direct imaging technique, if again Earths are common and we're given the go-ahead, we could find planets, let's say by 2.
Wow, that's very interesting. It's great to be living in this time.
It's great to be living in this time. And you know what I say now is, although it's my goal to find the other Earth, I may actually have to pass on the baton to the next generation. It's a multi-generational endeavor.
Yeah, and getting there would be multi-generational as well.
You mean traveling?
Yes.
Yes, traveling to another star. So what's funny is that before in the past, The search for exoplanets had a giggle factor. People would talk about searching for it and people would just laugh, oh, that's crazy, don't do that. And then, when exoplanets were found and believed in, the thought of traveling to another star had a giggle factor. It still does, actually. If you say, well, I'd like to go there, or send a spacecraft to another planetary system, it would laugh. But now, people are serious now. There are groups of people in the world who are trying to understand what it would take to travel to another star, whether that's us, or information about us, or a robotic spacecraft. And it's really remarkable to me how serious people are becoming about this. But yes, no matter how we can slice and dice space propulsion, it will be a multi-generational endeavor.
And we have sent radio signals there. I mean, our radio emissions, our TV emissions, and even directed messages sometimes. Directed.
In the past, our radio signals have leaked out. You know, now with satellite TV, we're actually beaming everything down to Earth. But our signal's out there. It's traveling through space. It's getting, weakens as it travels further and further from Earth. But we all have hope that someday, somehow, we will reach other planetary systems.
And their own radio signals might be stopping as well because they might be converting to satellite or other technology as well.
Right, perhaps they have a satellite network or underground cables. We don't know.
Now to conclude, what would you say to those who say, don't look up there, they're right here, right now, and maybe they're hiding?
It's funny you ask that because the other speaker tonight, Joe Nichols, will answer that question. In that case, what I respond is, personally, I have never seen any robust evidence that aliens or their spacecraft have visited Earth. And I know for some reason everybody wants to believe, because many people will say that actually, that they're already here, they're here all around us, I've seen them. But I can only say I just haven't seen evidence for it.